Strong acids and weak acids, strong bases and weak bases. You can have strong or weak of each. What do we mean by a strong acid? It doesn't mean that it can lift heavy weights, like a strong guy can lift heavy things. When we look at the formulas for hydrochloric acid and hydrofluoric acid, they look very similar. There's one H and one F. Here there's one H and one Cl. And fluorine and chlorine are right next to each other in the periodic table in the same family. And so we would expect these acids to be similar. But there's an important difference. HCl is what's called a strong acid, and HF is a weak acid. And this does not have anything directly to do with how corrosive or how dangerous or hazardous they are. When we say strong acid, we mean one that ionizes completely. So strong acid ionizes completely. Completely ionizes. A weak acid does not completely ionize. So let's look at this. When we put HCl into water, here we're representing it with chemical symbols, the element symbols. It comes apart, it donates a hydrogen ion to the water, and then the chlorides are floating around. And so what we have in here is hydronium ions and chloride ions. We do not have any hydrogen chloride molecules in the solution. Here it is with pictures, green representing the chlorine and white representing the hydrogen. When we put this in here, all of those combinations come apart. We have green balls floating around. The white balls are not floating around by themselves because hydrogen ions are only protons and they're too small to be out alone. They're going to ride on the water molecules. And so we'll see these hydronium molecules. Strong acids ionize completely. Strong acids are strong electrolytes. Do you remember what a strong electrolyte is? Or what it does? Does it conduct electricity? Yes, it does. Because there are ions in solution. And so it conducts electricity very well. When we look at concentrations of strong acids, HCl is a strong acid. A 1.0 molar HCl solution will have a hydronium ion concentration that's equal to 1.0 moles per liter, because all of it ionizes. When we have something in brackets, a chemical symbol in brackets, that means the molar concentration of X. So H3O plus in brackets means the molar concentration of hydronium ion. When we write this equation, we use a single arrow, meaning it goes completely to ions. It's not an equilibrium that's going both ways. Pure water doesn't conduct electricity. But when we put HCl in the water, it does. So here's pure water hooked up to a light bulb and electric current, but the electric current can't flow through the water. We put hydrochloric acid in there, it generates ions, and now the current flows and the light bulb goes on. And the light bulb glows strongly. It's a strong electrolyte. There are 6 strong acids. So we memorize the strong acids, and all the other acids are weak acids. So hydrochloric acid, hydrobromic acid, hydroiodic acid. So these are the halogen binary acids except for HF. And then there's nitric acid, perchloric acid, and sulfuric acid. Sulfuric acid is a diprotic acid, meaning it has 2 ionizable hydrogens. Monoprotic acids only have 1. Mono meaning 1 proton, protic meaning proton. Weak acids do not completely ionize. They contain few ions. Most of the weak acid is still as a molecule. So HF, when it's put in water, we have a double-headed arrow here. There's an equilibrium occurring. And the equilibrium lies pretty far to the left. We've talked about ionization constants. the ionization constant for, or the equilibrium constant for this reaction is fairly small, and so there's going to be a lot of HF, and there's going to be very little fluoride and very little hydronium ion. In pictures and symbols, here we've got the HF. We put it in water. We get some hydronium ions and some fluoride ions, but we also have a lot of hydrogen fluoride molecules floating around. Hydrochloric acid doesn't do that, but hydrofluoric acid does. Only a fraction of these molecules ionize. Most of them are present as molecules still. And so what we see is that it does conduct electricity, but weakly, not very strongly. It is a weak electrolyte. It has ions in it, so it can conduct electricity, but there aren't very many ions, and so not much current can flow, and so you get just this dim glow on the light bulb. Here are some common weak acids, but remember, any acid that's not on the strong acid list is a weak acid. Sulfurous acid is diprotic, as is carbonic acid. We can tell that by looking at the H. H2 is diprotic, H3 is triprotic. It has 3 protons that can ionize. So looking at these pictures, which of these is a weak acid? A, B, or C? Kind of have to look at it for a little bit before you can figure out what those things are representing. C is going to be the weak acid. Because in C we have these intact acid molecules as well as the ions and the hydroniums. Right? Over here in B and A, we only have ions. We don't have any intact acid molecules. So these are strong acids, and this is a weak acid. It ionizes partially. So here we're asked to find the hydronium ion concentration in each solution. And if the concentration is not specified for units, we're going to assume molarity. So 0.5 molar HCHO2. Is this a strong acid? HCl, HBr, HI, nitric, perchloric, and sulfuric. Is it one of those? No. This is a weak acid. Do weak acids ionize completely or partially? Partially. So we can't really say what the concentration is, except that it's less than 0.5. So the hydronium ion concentration for this acid solution will be less than 0.5, because only some of it will ionize. And with the information that we're given here, we cannot predict how much will ionize. That's a matter for Chem 1B. Any questions about that one? It only ionizes partially, so all we can say is that the concentration of the ionized portion is less than the concentration of the total acid in the solution. What about HI? Is that a strong acid? It is. Hydroiodic acid is a strong acid, meaning that it all ionizes. So this goes completely to H plus and I minus. So if we put 1.25 moles per liter of HI into this solution, we are going to get equal concentrations of H and I. This is like, a pair of shoes, right? If you have 10 pairs of shoes, how many left shoes do you have? 10. And how many right shoes do you have? 10. They're equal. There's one of these to one of those, and so you're going to get one of these for each one of those, and those concentrations are going to be equal to this. So the hydronium ion concentration, it's a pesky fly, go away, is going to equal 1.25 molar. What about 0.75 molar HF? Is HF a strong acid or a weak acid? It's a weak acid. So what can we say about the concentration of the hydronium ion? It's less than 0.75. Any questions? Yes?
The molarity increased or having greater than 50% in A, would that move from being a weak acid to a stronger acid?
That's a good question. No, it wouldn't. The weak acid, strong acid makes us think that a strong acid is more concentrated than a weak acid. That's kind of what we naturally think of. But it actually has to do with whether the substance ionizes or not. And that's a property of the acid itself. It doesn't matter how much of it is in solution. That formic acid will not completely ionize no matter how much you put in there.
Okay.
Yeah.
Because I had another question regarding F and Cl, because I was looking at the atomic weights of the elements and HF, HCl, and I was seeing if maybe it was based upon maybe the atomic weight or something, but as you said, it's something else that determines whether...
Yeah, what determines whether it's a strong acid or not is more complicated than we can get into in 3A. Strong bases are strong electrolytes, just like strong acid. It means that they dissociate completely. So things like lithium hydroxide, sodium, potassium hydroxide, strontium, calcium, and barium hydroxide. These guys are soluble hydroxides, right? Hydroxides were on that list of solubility rules. Lithium, sodium, potassium are all alkali metals. Generally, hydroxides are not soluble, but these guys are, and strontium, calcium, and barium are. With the diprotic acids, they lose their hydrogen ions one at a time, but these bases, these metal hydroxides, if they have two hydroxide ions like this one does, it will lose both of them at the same time. Sodium hydroxide is a strong base. We put it into water, it completely dissociates into ions. There's no sodium hydroxide molecules or chunks left. It all dissociates. Weak bases are analogous to weak acids. They do not ionize completely. There are not nearly as many of them. Really, I think the only one we're going to run into is ammonia. The most common ones produce hydroxide not because they have hydroxide ions in their formula, but because they accept a proton from water. And because water's donating the proton, then it becomes hydroxide, and that's how they produce hydroxide ions. So the general formula, or generic formula, is B, where B is some weak base, reacts with H2O. H2O acts as the acid, donates a hydrogen ion to the base. The base accepts it. Bases take the baby and watch it, right? And so this becomes BH plus and OH minus, and this is how it produces hydroxide ions in solution. This is what ammonia does. Ammonia accepts a proton from water and becomes NH4 plus. But this is in equilibrium, and most of it is still NH3. Only some of it is ammonium. And so that's why it's a weak base and not a strong base. It does not ionize completely. So when we see ammonia in water, there are a number of ammonia molecules and a few ions. That's a weak base. Organic amines are weak bases. We're not going to run across them very much. Bicarbonate ion can act as a weak base. It can accept a proton from water and form carbonic acid, which is unstable and dissolves into carbon dioxide and water. But that's why baking soda solution can feel kind of slippery, because it is somewhat basic. So ammonia and bicarbonate ion are the ones we're going to run into the most. So what's the hydroxide ion concentration of each solution? We've got barium hydroxide. Is this a strong base or a weak base? Strong base. All of the metal hydroxides are going to be strong bases because they will ionize completely, the soluble ones. So when this ionizes, what does it form? Forms barium ion, right? And hydroxide ion. How many hydroxide ions do we get? 2 of them. So if we put in 0.055 moles per liter barium hydroxide and it completely comes apart, each one of these makes 1 barium and 2 hydroxides. So what's the concentration of the hydroxide ion then?
2 to 1.
It's 2 times the 0.055, right? So one way you can think about this is 0.055 moles of barium hydroxide per liter. And we want to know how many moles of hydroxide. So we can convert barium hydroxide to hydroxide. You could draw the equation, you could write the equation like this, or you could look at the chemical formula. From the chemical formula, we see that in each of these formula units, we have 2 OHs. So we'll get 2 moles of OH for every 1 mole of barium hydroxide. Or you can think of it from the balanced chemical equation, 2 moles of OH for every 1 of these. I'm not going to trust my brain to multiply that. 0.11. Moles per liter, or molar, OH minus. Any questions? .05 molar C5H5N. Strong base or weak base? Weak base. It's not a hydroxide, it's going to be a weak base. Do we know what the hydroxide ion concentration is going to be then? Can we calculate it precisely? No, we can't. This is a weak base. It only dissociates a little bit. So just like with the weak acids, all we can say is that the hydroxide ion concentration is less than the concentration of the base.
And that's the way you refer to the answer?
Mm-hmm. Now, of course, it can be calculated, but not with the information we have presented to us in this textbook. We need an equilibrium constant. We need to do some other things. Is sodium hydroxide a strong base or a weak base? That's a strong base. And how many hydroxide ions for each unit of sodium hydroxide? 1. When this dissociates completely, we get 1 sodium ion and 1 hydroxide ion from each formula unit. And so the hydroxide ion concentration will be equal to 0.45. For A, it was twice as much because each of these units comes apart and produces 2 hydroxide ions. For C, it's the same because each of these units only has 1. So it's a 1-to-1 ratio. This is 1-to-2. This is a weak base. We have no information about how much of it dissolves, and so all we can say is that the concentration is less than 1.05. Any questions?